We're looking at an A2 paper from CCEA, and it is the Fields and Their Applications exam, and we're looking in particular at question 1, which is a gravitational fields question. So we start off 1A, what is a gravitational field? Nice, straightforward, remembering something from your notes. Remember, a gravitational field acts on mass. It causes a mass to experience a force. So a gravitational field is a zone where a mass will experience a force. Calculate the mass of the Earth if the gravitational field strength of the Earth's surface is 9.81 newtons per kilogram, and the mean radius of the Earth is 6.37 times 10 to the 3 kilometers. What we need to be careful about here is this radius of the Earth, because it's in a non-standard unit. The gravitational field strength is going to be gm over r squared, where m is the mass causing this gravitational field and r squared is how far out we are from the centre. So in this case we are exactly one radius out from the centre of gravity of this mass, so that's the r that goes into our equation. So just converting these kilometres, 10 to the 3 kilometres, into 10 to the 6 metres, we've got a radius of the Earth to go into our equation. So we've got an equation of g me over r squared for little g, and we just need to get me on its own. So me is just going to be g times re squared over big G. So mass of the Earth is going to be 9.81 times the radius here squared, just remember to square it, make sure it's in meters, over big G. And that gives us 5.97 times 10 to the 24 kilograms for the mass of the Earth. Part C then. GOES-10 is the name given to one of the geostationary operational environmental satellites that the USA uses to monitor weather. Its orbital radius is 3.58 times 10 to the 4 kilometers above the Earth's surface. Always watch when they say stuff like this, because that means that that's a height rather than a radius out from the center of gravity, so you need to watch that one. State the period of this geostationary satellite. So that's literally state the period. So that's not anything to do with these numbers. A geostationary satellite rotates with the Earth, so its period is going to be however many seconds there are in a day. So we've got 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. So multiply those together and you'll get the number of seconds, and it's 86400. GOES-10 has a mass of 2.1 times 10 to the 3 kilograms. Calculate the centripetal force required to keep it moving in its orbit. Remember that the mean radius of the Earth is 6.37 times 10 to the 3 kilometers. So remember that the height up to a satellite above the Earth, that isn't the radius of the rotation. The radius of rotation includes the radius of the Earth itself. So the height that we're given has to be added to the radius. That's why they remind us of that fact. So the radius of the orbit up to where the satellite is here, it's going around, that consists of these two numbers being added together. So our orbit equals re plus the height h that they've given you. And we also know that the centripetal force on an object will equal mv squared over r, or mr omega squared. Now in the case of this one we know the angular rotation period, so we're better to work with omega. And omega can be worked out because the thing goes the whole way round, which is 2 pi radians in a time of its period, big T. So you can write omega as 2 pi over big T. So the equation becomes mr times 2 pi over big T all squared. And so we've got the mass going in, make sure it's in kilograms, yes it is. The radius values have to be converted into meters, so 10 to the 6 for this one, and 10 to the 7 for this other one, because it's 10 to the 4 kilometers is 10 to the 7 meters. And then 2 pi over 8640, the number of seconds in one period. And then we need to remember to square that. Just check that everything's in the right units and then put it through your calculator. And that comes out at 470.56 newtons, so we'll call it 471 newtons. So when the satellite reaches the end of its useful life, it is boosted out of its geosynchronous orbit into a higher orbit. Determine the satellite's new period if the new orbit has a radius of 6.22 times 10 to the 4 kilometers above the Earth. Now this kind of question can be done by ratios if we remember that Kepler found that t squared was proportional to r cubed. So if t squared is proportional to r cubed, that means that t squared over r cubed, or r cubed over t squared, whichever way you want to write it, is going to be equal to a constant. So we're interested in a period, so I would write t squared over r cubed equals a constant. And how does that help us? Well, we have initial conditions of a known period of 1 day and a known radius, which we worked out by adding the radius of the Earth to the height. So basically what we can do is introduce this third radius to an equation where t squared over r cubed for the first conditions equals t squared over r cubed for the second set of conditions. So if t squared over r cubed is a constant, then t1 squared over r1 cubed will equal t2 squared over r2 cubed. So we know these things from the first part of the question. We are interested in this, and this is just found using the new number and the radius of the Earth. So there's only one unknown. So these two numbers here just come from the first part. So T2 is the one we're trying to find, and R2 is just again the radius of the Earth added to the meters version of this number. 6.22 times 10 to the 4 becomes 6.22 times 10 to the 7 when we write it in meters. So you've got this ratio and you solve it now for T2 because you know all the numbers in it except T2. And when you do that, you get T2. And that comes out to be 179,786 seconds. So to 3 significant figures, which is the only accuracy we had in the original numbers, we'd quote that to 1.80 times 10 to the 5 seconds. Okay.